Welcome back to Math 155. Today we are embarking on the final section of this course, which deals all with things to do with discrete mathematics. Now, why do we care about discrete mathematics? Well, there are lots of things in the real world that can't be treated as being continuous. So we've been thinking a lot about continuous things like continuous functions that we can take derivatives of, or that we can integrate. Now we're going to be thinking about discrete things that can't be treated in this continuous manner. So as an example here, we've got human insulin, which consists of two peptides. These peptides are chains of amino acids, and each of those amino acids is a discrete thing. So we have one chain that is 21 amino acids long and one that is 30 amino acids long. And there are 20 different types of amino acids. So we can think about all the possible combinations and permutations of amino acids that we can have to form these different peptides that will create other things other than human insulin. So let's dive right in and think about the ways in which we can count possible outcomes. So for example, if you roll a dice and flip a coin, how many possible outcomes are there? Well, if you roll a dice, there are 6 possible outcomes, assuming it's a normal 6-sided dice. And if you flip a coin, there are 2 possible outcomes. So if we multiply these two things together, that gives me the total number of outcomes that we can have, the total possible outcomes that we can have. The way of thinking about this is to think about tree diagrams. So when I do the first thing, which is roll the dice, I can get a 1, 2, 3, 4, 5, or 6. And then for each of these, when I flip the coin, I have heads or tails. And then if you add up all of these branches, you'll get 12 possible outcomes. So in general, if we have if we have 2 ordered tasks and we have n1 possible outcomes for task 1 and n2 possible outcomes for task 2, that means that we just multiply those 2 things together, the n1 and the n2, and that gives me the total possible outcomes for these 2 different tasks. Okay, so let's apply this to a simple problem and think about what happens if we have more than 2 possible outcomes. So at a pizza parlor, there are 3 possible choices of crust, 5 choices of toppings, and you can either order a pizza with or without cheese. So if you only want 1 topping, how many different choices of pizza could we possibly have? So here we just need to write down how many different types of crusts, in this case 3, multiply it by the different toppings that we have. So there are 5 possible toppings, and we can have it with or without cheese. So there are just 2 options there. So 5, 3, and 2. Multiply these together, we get 30 possible outcomes. So this is just an extension of the case above with the dice and the coin. If we have any number of tasks, if we have m different tasks, we just multiply all the possible outcomes for those m different tasks to give us the total number of possible outcomes for all of those things put together. Okay, so that's the multiplication principle. We can now think about things called permutations, and a permutation of a set of objects is an ordered arrangement. This ordering is really important here. The ordering of our things without repetition. So this is the other part that's really important. So in the example here, we are asked to enumerate all of the possible permutations of 3 symbols, 1, 2, and 3. You could also think of these as being 3 objects, an apple, banana, and a pear, say, and you eat them in a certain order, perhaps. So you have all the possible permutations of these symbols. Well, what do we do? One way of doing this is to, first of all, write down all the things that we can have in the first possibility. So we could choose 1, or we could choose 2, or we could choose 3 as our first thing. If we choose 1 first, then we could choose 2, or we could choose 3 next. So I'm going to put a 2 there. Again, we can choose 3 as another option here. Likewise, with 2, we can choose 1 or 3. Remember, there's no repetition here. So we have 2, and then 1. We can have 2, and then 3. And then for 3, we can have 1, or we can have 2. And then in our final column, we're just going to have the one thing that we haven't chosen yet. So in this case, we have 3, 2, 3, 1, 2, and 1. So there are 6 different permutations of this set of objects 1, 2, 3. And these are all the possible permutations that we can have. So in general, how do we work out the number of permutations that we can have? Well, we use something called the factorial. So a factorial of any positive integer n, so n has to be a positive integer, so that's 1, 2, 3, 4, and so on. We define n with this exclamation mark after it, that means n factorial, as just being the product of all the numbers from n down to 1. Okay, so for example, if we had 4 factorial, that's going to be 4 times by n minus 1, which is 3, times by n minus 2, which is 2, times by 1. Okay, so we multiply these things together, and you'll get 24 in this case. So you can see that n factorial gets very big very quickly as we start multiplying these things together. That's because we start having lots of different possible outcomes if we have a large number of things n. So we say that the number of permutations that we can have for any set of objects is n factorial. If we just go back to this example above here, we had n is equal to 3 here. So if we think about 3 factorial, that's 3 times by 2 times by 1, which is equal to 6, which is the number of permutations that we had above. Okay, so this is our total number of permutations. One way of thinking about this is if, suppose you have n individuals, and if it's hard to think about n as just being any number, think of, say, 10 individuals, and there are a matching number of objects on a table. So they are, say, 10 individuals with 10 objects, or more generally, n individuals and n objects, and they go up in order and they pick one of those objects at random. So the first person goes up and they can choose from any of those objects on the table. So there are 10 objects, so they choose one of those 10 objects. So there are 10 possible choices for that first person. And then the second person goes up, and because the first person has taken one of those objects off the table, now there are only 9 choices. The third person goes up, now there are only 8 choices, and so on. So if we want to work out the possible permutations, we need to work out 10 times by 9 times by 8, and so on, all the way down to the last person who only has one possible choice because there's only one thing left on the table. So this is 10 factorial, and that gives us the total number of permutations that we can have. So if it's easier, think about a group of people going up to a table and picking objects off that table without repetitions. They're not placing them back on. So mathematicians often talk about these ideas of permutations in terms of jars or urns with colored balls in them. The reason they do that is because it's a simple way to think about these things without having to necessarily think about a lot of the detail you'd have in the real world. But these kinds of ideas where we're taking balls out of an urn or socks out of a drawer or things like that, they're essentially thought experiments to help us think about real world problems. Okay, so although we'll be learning some of these ideas in terms of balls in jars, they can be applied to lots of interesting cases when it comes to things like experimental data. Okay, so here we've got a jar that contains 4 different colored balls, red, blue, green, and yellow. And we're going to remove one ball at a time until the jar is empty. So we're not replacing them back into the jar. So how many different sequences of colors are possible? Well, there are 4 different colors here. So the first thing I could pull out, suppose it's a red. Then the next time I pull something out, I can't pull out a red again. There's only blue, green, and yellow left in there. So this time there's going to be 3 things. Then my third pick, there's only going to be 2 balls left and then 1 ball left. And this is my 4 factorial that I mentioned above, which is equal to 24. So there are 24 different permutations, 24 different sequences that are possible. Now let's think about, rather than taking all 4 of those balls out, and there are 24 possible combinations, what happens if I just take out 2 balls? Again, not replacing any of those balls into this jar. So in this case, the first thing I draw is going to be, there are going to be 4 options for it. So it could be red, blue, green, or yellow. And because I've taken one of those away, the second drawer, there's only going to be 3 options. We're only drawing 2 balls, so we haven't got those additional steps that we had above. So here we have 12 possible combinations when I have 4 balls in a jar, at different colors, and I just take 2 of those out in sequence. Okay, so we can generalize this idea to what happens if we have any number of objects n, and we take k of them out at a time, and we care about the sequence in which we take them out. So we care about the permutation. So the way we calculate this, the permutation, when we have n objects, a total of n objects, and we're taking k of them out, note that by definition, k has to be less than or equal to n. We can't take more objects out than are in the jar in the case above, or just in a general list of things. How do we work this out? Well, it turns out that first of all, we have n choices for the first thing. Then the second thing, we have n minus 1 choices. This is just like the different colored balls in the jar above. Then n minus 2 choices, and so on, all the way down to n minus k plus 1. Okay, so this is taking out k of those objects. There are, here we're multiplying together, a different choices. So what happens when we actually try to calculate that? It turns out this is equal to n factorial on the top divided by n minus k factorial on the bottom. And this gives us the total number of permutations when we take a objects in a sequence out of a total of n possible objects. So if I go back up to this example here, if I calculate n factorial over n minus k factorial, so we have 4 objects, so that's 4 factorial divided by 4 minus 2 factorial. So this is 4 factorial over 2 factorial. This is 4 times by 3 times by 2 times by 1 over 2 times by 1. You see that this bit is going to cancel with this bit. So we just have 4 times by 3, which is 12. So this is the same answer that we had before. So this is our permutations as a general formula. And there are a couple of things to note. One is that if we have k equal to n, we just have n factorial. We have all of our different balls that we're drawing, so that's this example here. And if we withdraw no balls, if k is equal to 0, we have 1. So often a thing that will come up is how do we define 0 factorial? What does 0 factorial mean? Well, one way in which we can define these factorials is to think about n factorial as equal to n times by n minus 1 factorial. So we take n minus 1 factorial, we multiply it by n, and we get n factorial. Okay, so what happens if we let n equal 1? So we have 1 factorial is equal to 1 times by 1 minus 1 factorial. So this is 1 factorial is equal to 1 times by 0 factorial. So it's just equal to 0 factorial. So 1 must equal 0 factorial, okay? So this formula really comes into its own when we want to take a small number of objects from a much larger pool of objects. So for example, how many 5-letter words with no repeated letters can we form out of the 26 letters of the alphabet? Note that a word here need not be in the dictionary, so we're going to count any permutation of letters as being a word, not necessarily English words or German words or French words. Okay, so if we have 26 letters in the alphabet and we're choosing 5 of them, our n is 26 and our k is 5. So this is going to be 26 factorial over 26 minus 5 factorial, which is 26 factorial over 21 factorial, which is 26 times by 25 times by 24 times by 23 times by 22 times by 21 factorial. The reason I've stopped there is because I have a 21 factorial on the bottom, and so these two things cancel here. So we're not going to work out what that is. That's quite a large number anyway, but at least we didn't have to work out n factorial and then work out n minus k factorial and then try and cancel these. We always have some sort of cancellation going on here. Okay, that's it for today's pre-lecture. Make sure you're familiar with these terms permutation and factorial. We'll be using these going forwards. Okay, thanks very much.